Hi gang, welcome to Computer Graphics. Today we're going to be talking about polygon filling. We're going to be finishing that up from last time, and we're going to be talking about the Z-buffer algorithm as well. So remember, this is the section of the class where we're trying to make objects appear solid. So that's kind of the general idea of what we're doing here. And I'll also show my version of the program running so that you can see that, yeah, it's doable, it is possible. I think I want to start really quick by bringing up the syllabus again, just so that we can see where we are. So today we're going to finish up polygon filling and do Z-buffering. We're here on the 22nd. And then on Monday, we'll do a lecture about color and reflection. And basically, I'll attempt to convince you that color doesn't really exist as a unique, unambiguous concept in the real world. So that's the point of Monday's lecture, is to try to convince you that color is just a figment of the human imagination. But importantly, next week on Wednesday and on Friday, that is when we have our midterm project presentations. So you guys need to be making progress on those, because those are going to be done on Wednesday and Friday. And remember, these are, 15, 20, really 20 minutes, including questions long. So so that's important. I'm getting the question for, do we know which groups are going on which days? I'll probably go. I don't know. To be honest with you, if you look at the requirements, they're all due at the same time, right? So you have to have all your projects prepared and sent to me ahead of time, and so it's all due on Wednesday. Otherwise, it wouldn't be fair if I said, oh, half the students get an extra 2 days to work on it. So everything's due on Wednesday. Whether or not you give it on Wednesday or you give it on Friday isn't going to make a big difference. That's the only fair way to do it, really. And then after that, you guys are going to still be working on the current assignment. But we'll talk about what are called illumination models, and we'll talk about shading models. So right now we're trying to make objects look solid. As we look ahead, we'll be trying to make objects not only look solid, but make them look realistic. So we model objects as polygonal, structures. But the world, doesn't exist. Generally, our objects don't exist of flat planar polygons. So the question is, how can we take objects that internally we're representing as, a structure of flat planar polygons and paint them in a way that makes them look more realistic, make them look, rounded, for example, gives metal-like objects a shininess to them. Those are the kinds of things that we're going to be doing looking forward. Okay? All right. Any other questions about any of that? If not, let's bang on into the lecture. Because I usually don't require attendance in class. I leave it up to students to decide whether they're getting useful information out of the lectures themselves. But I've taught this class a bunch of times, and I know how challenging parts of it can be, and I know how critical the lectures are to be able to do those parts. So you're shooting yourself in the foot, if not the head, if you don't attend lectures. Now, of course, I'm talking to the to the people who are here and not the people who need to hear this message. But the 7 people, the 1/3 of the class that isn't here, they're doing themselves a great disservice. You might want to get the word out that if attendance continues to be sporadically low like this, I may start giving just pop quizzes in class as a way to encourage attendance. I hate doing that, but I also hate failing students, and I hate when they come to me and they're crying about their program, or they're asking me questions at 3 in the morning on email about their program that we covered in class, and they never bothered to show up. But then they think they can ask me at 2 o'clock in the morning before their program is due, hey, Mike, can you help me out on this? And I like to be a good guy, and I do like to help out people. And please, if you do have a question, I'm not saying don't send it to me by email. Please, please do. I'm just saying that it is kind of annoying when I realize that certain people don't show up to class, and then they expect me to be available, literally at all hours. So I find that I don't get mad anymore. I find it funny. I go, immature. That person's going to have to grow up if they're going to survive in the real world. But anyway, enough of me bashing you young people. Okay. Young people bashing. It's what old people do. Okay. So we're doing polygon filling. Here's a polygon. It's a triangle. We're going to build our polygon fill algorithm so that it's general enough that it can handle any simple polygon that is convex. And remember, we described what that meant last time, right? Where we talked about, polygons. We mean polygons like these guys, and we don't mean polygons like these guys. And what makes these polygons special is that you pick any 2 edges. It doesn't matter which one of these things you're looking at. You pick any 2 edges, and you draw a line between those edges, and all of the points of your line will be in the inside of that polygon. If you look at these kinds of polygons, these concave polygons, that's not true. If I draw, this is an edge and this is an edge. If I draw from this edge across, well, I cross other edges, right? And I spend part of my time outside the polygon. So we want to build a polygon fill algorithm. It's much easier if we restrict ourselves to convex polygons. And in reality, almost everything are triangle meshes these days. But we're going to keep it a little more general. We're going to do triangles and rectangles because some things are actually a little easier to paint or a little bit easier to define if you allow yourself to have rectangles. Like our pyramid, it kind of makes sense to make the base a rectangle rather than split that up into two different triangular polygons. You could do that, but it's not. It's just kind of wasted. Okay, so last time we started talking about some standard things to do polygon filling. We're going to fill from the uppermost vertex to the lowest vertex. How do you know the uppermost? It'll be the vertex with the smallest y value. So if we look, this is a y value of 0, this is a y value of 20, this is a y value of 30. 0 is the smallest, so the vertex with the smallest y becomes the vertex that you're going to start at. Assuming there's one vertex, there might be, if we had if we were doing a rectangle like this, and you try to say, well, what about this line? We're going to have to worry about that. But if you talk about these two vertical lines, right, there are two separate points that would have the lowest y value in them. So it's not always one single point that has a lowest y. There could be two vertices with a minimum y that are equal to one another. That's starting to get to, so while the algorithm itself is easy to understand, fairly easy to understand, there's a lot of edge cases that you have to program around. But most of the time, especially if you have triangles, most of the time there will be a single point that will be the highest point. As I just showed you, that's not always the case. If you've got a cube, you could have two parallel vertical lines where both of them have where there are two vertices that have the smallest y value. But let's just worry about this case right here, right now, where we have one vertex that is the highest, that has the smallest y value. Okay, so we're just given a list of vertices, right, for a polygon, and we're asked to fill it. So we've already, played around with the idea of, well, from those points we can learn a lot of stuff. One thing we can do is we can obviously get the edges, since the point list is ordered usually clockwise. So it's in this case I have it A, B, C. It's a clockwise orientation. And I didn't call this one A. I called this one A just to illustrate the fact that the first polygon the first vertex that you list is not always going to be the one with the smallest y. In fact, as you rotate the object, right, even if we had started out that A was up here, maybe that was the case, but we just rotated this polygon, right? So as you move it, as you rotate it, whichever point has the smallest y, that's going to change, right? So you don't assume that the first point in the vertex list is going to be the one with the smallest y, because if it's a triangle, you got a 1 in 3 chance. that's it. So in this case, it was the second point we defined. It was B. So you might say, well, aren't the lines that make this up? Wouldn't you have defined them something like A, B, B, C, C, A? Probably. That's probably how we drew this thing when we were drawing it. But we're not drawing anymore. We're filling, and in polygon filling, we have to fill. We're going to fill a fill line at a time, going across and going down vertically. So that means that edges have to be defined from the vertex with the smallest y value to the other vertex. So this isn't line AB. This is line BA, right? Because B has the smallest y. So BA is one edge, and BC is the other edge. And this final edge here isn't CA, it's AC, because A has a smaller y than C. So you're always going to draw your edges or define your edges. We're not really drawing the edges, we're filling between them, but we have to know where the edges are. The edges are defined from the smallest y to the other vertex, which will have a larger y. So the edges in this case are BA, BC, and AC. Let's see if there's a question here from Eric Pitts. So for polygon filling, we are going to have to start storing the projected display coordinates, I assume. You'll have to compute them, and in the polygon fill algorithm, they'll be stored. Yeah, but they're not like stored globally or something like that as part of the polygon definition. But when you get to the fill routine, yeah, you'll have to have these. Andrew asks, the convert to display coordinates function will still convert the vertices correctly, right? And the answer to that is, yeah, of course it will. And before you convert to display, you'll have to project. But we've already done the methods for doing both project and convert to display. So we have those tools in our toolbox already. Okay, so edge BA, edge BC, edge AC. Edges, lines, have a fixed slope, right? slope is slope is defined as y's over run, right? The difference in y end minus y start, 20 minus 0 over x end x start, so 10 minus 30. So the slope of this edge is minus 1. It's 20 over minus 20. Slope of that edge, well, I'll draw it this way. The slope of that edge is minus 1. What's the slope of this edge? Well, this edge is vertical. So, in fact, 30 minus 0 is 30. That's the change in y, right? Over the change in x. Unfortunately, x is 30 here and x is 30 here. 30 minus 30 is 0. And now we have a bad old problem because we've got 30 over 0 and that's not really defined. Essentially, it's an infinite slope, right? Okay. So vertical edges have infinite slope. But really, and why are we interested in slope? Well, really, we're not interested directly in slope. We're interested in the inverse slope. Let me go and grab this image down here. Got to scroll. We'll come back to some of these formulas. We'll come back to these formulas. But what we really want is we want the change in x, dx. And dx basically says is as I move down a fill line, what happens to my x value? Because you see, I'm going to go a fill line at a fill line. So my y value is going to increase by 1 each time from what it was previously, because I'm going down a fill line, right? So the y is going to change by 1. Well, if my y changes by 1, what does my x change for this edge, and what does my x change for this edge? Because I want to draw a fill line, so I've got to know, I know what line I'm going to draw, right? I'm going to start at this y here, the smallest y, which is 0, and I'm going to go to the line with the largest y value, which is down here. So I've got a little loop that's going from line to line, right? So I know my line number, I know my y value for these pixels that I'm going to draw here, but I don't know yet where do I start filling and where do I end filling. So there's going to be an inner loop, essentially, that's going to drive you across the line. There's going to be an outer loop that'll drive you from line to line, from fill line to fill line. And then there'll be an inner loop that goes from x start, essentially, to x end. Well, how do I find these values? Well, whatever my value was here, my x value, it's going to be 30, right? Well, each time I go down a line, I add my previous value, I add to it my inverse slope, in this case, dx. So I add minus 1. So this is from 30, 0 to 30, 0. It's the vertex, so the line is 1 pixel, right? But when we get here, right, it's 30 minus 1, so it's 29. So from the pixel 29, 1 to the pixel 31. Okay, well, why is that? Why is it 31? Well, I'm doing this line right here because how much do you change y each time for this edge? See, you've got to know where you're going to start, so that's one edge, and where you're going to end, that's determined by the other edge. So I need the change in x for edge BC. Well, that's 0, right? Remember we had it's the inverse slope. So the change in x, 30 minus 30, over the change in y, 30 minus 0, right? So 0 over 30, it means basically you're saying there are 30 steps here, and we have to change by a total of 0 in x. So 0 over 30 will change by 0 each time. That's basically what you're telling me. So I'll add 0 each time I do an edge here to get my ending point, but that's not going to change it. So this is, like I said, 29 is x, 30 is the end x, and then we go 28 to 30, 27 to 30, 26 to 30. And you can see I've got a little thing here. It's 30, 29, 28, 27, 26. We're just subtracting one from our current, our previous X each time we go down. Does that make sense? It's really very straightforward. The details can get a bit much. So again, this is showing it here. You know, the actual individual pixels. So, because when I say I'm going to draw a horizontal line, I'm not going to use the built-in line fill. I'm going to actually set a pixel at a time and do this manually as I move across here. You might say, why are you doing that, Mike? We're doing it like this because when we get to the next section, we're going to be setting the colors of every individual pixel separately. So we want to go ahead and be drawing our pixels separately now. Okay? Additionally, you have to treat each pixel individually separately if you want your Z buffer to work properly. Okay? So if we were just painting, you might say, oh, I'll just use the built-in fill line command between the start and the end, right? But we're not just painting. This is the step after this is to do Z buffer. So we have to have it a polygon at a time, or a pixel at a time. Okay. So these equations look a little bit intimidating. They're not. This is just the dx that I was talking about, the x end minus the x start over the y end minus the y start. Yeah, I got a lot of subscripts because we've got to deal with the left edge and we've got to deal with the right edge. And when we get to Z buffers, we got to deal with going across. So that's another set of these formulas. So this gives you the overall change in x. Where do you start? You start at the starting x value of the first point, the point with the smallest y, and that gives you the first value, right, for, in this case, the left edge. And then from that, say for fill line I starts at 0, you can compute fill line I plus 1 by adding in the dx. This is just in math form what we just talked about. So that's for the left edge. You got to do the same thing for the right edge. These are exactly the same formulas. I just changed the words left, the word right here. Okay. So that gets us the information about the two edges, and then all we have to do is we have to fill across. Well, that's really, really easy, because what happens when you go from pixel to pixel? What happens to your x value? Well, you're just adding 1 each time as you move across the line, right? So if I'm starting at, let's see, that's 29, 28, 27. If I'm starting at 27.3, right, well, then the next one is going to be 28.3, 29.3, 33. I'm just adding 1 to the x value every time as I move across the fill line. So you get started on your fill line by your first pixel, pixel 0 that you're painting on the fill line will be the x value for the left edge. Because we're going to always paint from left to right, from left to right, from left to right. So that gives us where to start. And then as we go across, subsequent x values are simply plus 1 to the previous one. So that makes sense. Again, we've got a lot of balls in the air right now, but there's nothing complicated about any of those balls. This picture basically sums up the whole thing. Are there any questions about it? Any part of it that doesn't make sense at this point? Any part of this that doesn't make sense? Okay, so now that we kind of know what we're going to do, we want, because it's computer graphics and speed is everything, we want to do this in the fastest way possible, in the in the most efficient way possible. Okay. So what we're going to do is we're going to pre-compute some values and store them in a table, the polygon fill table. And that table is going to basically have constants in it for that particular polygon, information about the edges in the polygon. We'll pre-compute those, and then you'll use those values. Now, what am I talking about? Well, let's go back to the equations that we talked about. Well, if you're going to draw any polygon, you've got to have its vertices, right? So when you're going to fill a polygon, you're going to need to know the vertices. At least you're going to need to know, well, you're going to need to know the vertices to compute the stuff we're going to compute. You need to know the smallest y value. We already talked about that, right? Because that's where you're going to start. That the smallest y value of all of your vertices tell you what the first fill line will be. So why not compute that and store it in a table, right? And then we also need to know the largest y value, because that's going to be where the end of your outer loop is, your loop that's going to fill by line to line. So I need to know my y start and my y end, because that's going to basically tell me where we're going from. For each edge, the dx, the inverse slope, is fixed for an edge, right? Edges, the slope doesn't vary. That's the whole point of what makes an edge an edge. It's got a constant slope. So, and therefore a constant inverse slope. So we can compute the dx value for each edge and store it in a table so that we've got those dx values. So with that information, we can then go into a polygon fill algorithm and not be recalculating stuff you don't need to recalculate. So if we do it first once, that'll be good. So we end up with a table like this. For each edge, we have an entry. So we've got an edge table, and there's an entry for each edge. We need to know the starting x and y values for each edge. So now don't think this x start means this is the point here, and the x end means this is the point here. That's not what this x start and x and x end is. What we're trying to do is, before you can even worry about fill lines, right, you have to be able to define the start and end points. So this is basically saying, okay, for edge BA, right, BA has two endpoints, 30, 0, and 10, 20, right? Which of those is the starting endpoint? Well, its starting endpoint is 30, 0, because you have two of these, 20 and 0, those are the y values, and you start at the smallest y value. So y start is for edge BA is the smaller of the y values of its endpoint. X start is simply the x value that goes with the y that you computed. So the point here is 30, 0. The start point of edge BC, of course, you're going to go from the smallest to the largest y. So again, the y is 0, and of course the x is 30, 0, because edge BA and edge BC share the same vertex. How about edge AC? Well, you got a 20 and you got a 30, 20 smaller, so 20 is the y start value, right? And what's the associated x that goes with that? 10. Okay, so this is essentially the xy of the starting point of edge BA. This is the xy of the starting point of edge BC. This is the xy of the starting point of edge AC. What is y end? Y end is the y value of the other vertex of that edge. So for edge BA, the starting point is 30, 0. The ending y value is 20. It's the y value of the other endpoint. We could have saved x start in this table too, and sometimes that makes things a little easier, but we'll see in the algorithm we don't actually need that value. You might say, why don't you need that value, Mike? Well, because we're going to compute the inverse slope. You're going to need the x value here to get the inverse slope, but you don't have to store the x end value in the table necessarily. So we compute the inverse slope, right? That is our change in x over our change in y. And minus 30 is minus 20. 20 minus 0 is 20. Minus 20 over 20 is minus 1. We store that change in x, that dx here for edge BA. We do the same thing for edge BC. We do the same thing for edge AC. Then we take the table and we sort it by y start values. After we've computed the information on each of the edges, where the edge starts, the xy of the start point of the edge, the y value of where the edge ends, and the inverse slope that lets us move, calculate our x each time we move down one line, okay? After we have all that information for the edges, we sort our edges by y start. Why do we do that? Because we've got to say, okay, I've got 3 edges. I got 3 edges in an edge table. Great, but I need to actually draw a fill line from an edge to another edge. Which 2 edges do I draw between? Well, I'll draw between the first 2. Who are the first 2? It's the 2 with the smallest y start values. Those are the edges I'm going to draw between. Now, in this case, they happen to both share the same vertex here. But as we continue to fill, we will notice that there will come a transition point here. How are we going to handle that transition point? In this case, edge BA needs to drop out of the fill process and edge AC needs to come into the fill process. The way we do that is when you reach the y end value, for one of your 2 active edges, you'll always have 2 active edges. When you reach the y end value of one of your 2 active edges, you switch, you drop out that edge and you choose the next edge in the table. So in that case, we would now be drawing between the edges BC and AC. So that's giving us, by sorting these things, we know where to start, which 2 edges to start between, and the y end tells us when you drop out, right? When an edge drops out. And when that edge drops out, you need to replace it with the next edge in the table. There's one other little tweak that we got to know about, or one other little feature that we got to know about. The edge table, I showed BA coming before BC. And I did that because visually we know that BA is the left edge and BC is the right edge. Algorithmically, you don't know which of these edges. You know the first 2, because the y value, the y start value is telling you you're going to be drawing between these two edges, right? Because these are the two edges with the smallest y. But it doesn't tell you which of them is right and which of them is left. Basically, to do that, you'll have to look at the x values. And the smaller x is the left, and the larger x is the right. Which brings you to the point of saying, but Mike, they're both 30, and neither of these 30s is smaller than the other 30. And that's true because the first edge we're going to draw, it doesn't matter which you think of as the left or the right edge, because you're drawing from 30, 30 to 30, from 30, 0 to 30, 0. All right? You're drawing one pixel. You're starting and ending up the same spot. It doesn't matter which of those edges you thought of as left or right. But when you move down to the next edge, you will subtract 1 from 30, giving you 29, right? You will add 0 to 30, giving you 30 for the next edge. And now you can see that one of the x's is smaller than the other x, and that's how you will know that this is the left edge and this is the right edge. Okay? So again, nothing's hard here. There are just a lot of balls in the air, which is why I can't believe that 7 people decided to skip this lecture. There are a lot of balls in the air. So, what's the purpose of this table? The purpose of this table is to pre-compute some information about each edge, because we're going to want to draw between edges. We sorted the table by the y start values because we're going to start from the edges with the smallest y and work our way towards the edges with the largest y, from smallest to largest. So that's why we sorted it. How do we know which edges we're going to draw between? You're going to draw between the first 2 edges to start with, okay? You don't know which of these is left or right. Every time you're going to draw an edge, you have to check to see which of the edges is left and which of the edges is right. You do have to do that every time you draw a line to see which of the 2 active edges is left and which is right, because when you reach a transition point like this, in this case, the left edge happened to drop out of the table. But if this polygon had been oriented differently, the right edge might have dropped out of the table, okay, or been replaced with a different edge. So that's the way that works. Okay, some things about polygon filling. We've talked about some of these. Edges are defined from a start point with a smaller y to an end point with a larger y. Thus, the AB edge is defined from B to A, blah, 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 blah. The starting point of an edge will be referred to as x start, y start. You can see that here in the table. Edges are sorted by increasing y start values. We talked about that and why. Fill lines are always drawn between the 2 active edges, but edges are not ordered by leftness and rightness in the table. Before drawing each fill line, you will need to check which of the active edges is left and which is right. Y end is the y value of the end point of the edge's vertex with the larger y value. Every edge is going to have a start vertex and an end vertex, right? The smaller of those will be y start, the other will be y end. The change in the edge's value from horizontal fill line to horizontal fill line is dx, which we defined as the change in x over the change in y. What will be the, this is for the entire edge, so that gives us the dx. Here's something new. Horizontal edges are not entered into the table since they can be neither a left edge or a right edge. Okay. Remember when we were thinking in terms of slope before we flipped it to get dx? We said that, well, vertical edges are problematic if you're talking about slope because they have infinite slope, right? There is no there is no slope for this line. It's infinite, right? Because you'd be dividing by 0. But when we flipped things over, we're interested in the change in x as we change y. Well, what happens if you have an edge that's horizontal, right? The opposite of vertical. It's a horizontal line. Well, if you've got a horizontal line, let me see if I can, like this triangle here. This is a horizontal line. Well, what's the change in y? There is none, because there's no vertical change in y. This is a horizontal line. And so you'd run into exactly the same problem when you ran into with slope, right, where you're trying to come up with the dx. The dx would be infinite because you've got a 0 in your denominator. So edges that are horizontal are not entered into the table. You might say, well, isn't that going to cause us not to draw the bottom edge, or in this case, draw the top edge? Because remember, it can be the orientation of these polygons can be absolutely arbitrary. Your algorithm has to work no matter how it's oriented. It's not a problem, because remember, what we're doing is we're painting fill lines that go across, right? So the last line you draw will be from this point to this point. This just becomes a fill line. Ta-da! So this line is going to be drawn. It's going to be drawn as the last fill line, right? This line is going to be drawn. It would be drawn as the first fill line. Now, when we were in the example we were using just above, right, it was a polygon. It was a triangle like this that had one start point. So the first edge was, from 30, 0 to 30, 0. It was a single pixel. Well, if your polygon's oriented like this, so that there's a horizontal line on top, obviously you won't be drawing from 30, 0 to 30, 0. You'll be drawing from, I don't know, maybe this is 10, 0 to maybe this is 40, 0. I don't know, but the x value will be different, and you will do the fill line. Okay. Because you don't enter horizontal edges into your table, your polygon table may have 3 edges, and normally most of the time will have 3 edges, but could have as few as 2 edges if you had a polygon that was oriented like this or like this. Does that make sense? What I'm saying here, in other words, is you can't depend on your table having some fixed number of values in it, even if you were just sticking to triangles. So you might say, well, if I've got a triangle, then I'm definitely going to have 3 edges in my edge table, in my polygon fill table. No, you could have 2, because we don't enter horizontal edges. What about a rectangle? Same kind of problems with a rectangle. Normally, you would think that you would have 4 edges in a fill table for a rectangle, but in this case, 2 of these edges are horizontal, so there would only be 2 edges in the table. And think about it. If I'm going to fill this puppy out, really, I've got a start and an end, and I'm just drawing between them, so you really only need 2 edges. Now, again, most of the time, it's going to be in an orientation so that there's going to be 4 edges there. Here's a practical detail. Very short and thin, or very tall and skinny polygons that are viewed almost edge-on, where their height or their thickness is less than a pixel, may generate an empty fill table, even though those polygons may technically and mathematically be forward-facing. What are you saying here, Michael? If we were dealing with the world of perfect numbers, we wouldn't have to worry about this. But when we're dealing with x, y, and z's in 3-dimensional space, we can talk about x at 32.7632185. We can have our x and our y's and our z's at any precision we want. But when we go to render that point as a dot on the screen, we don't have the choice of going to pixel 32.7385 or whatever the hell I said, right? You're going to either go to polygon 30, x of 32 or x of 33. So you can have a polygon, right, that back of my hand facing away from me, facing towards you. Well, what happens as we rotate? At some point, you can get a very, very, very thin, you can just see the top of my hand here. And you can just see the top of my hand, and now you can't. Well, at some point, that polygon that represented the top of my hand there, you're viewing it almost edge on. It's still slightly towards you. So the math that you're doing in real numbers says, oh yeah, it's a forward-facing polygon. When you do the polygon cull test, it comes out and it says, yeah, it's forward-facing, right? You got a positive, you got something greater than 0, right? In our little test, our polygon, backface culling test that we did 2 lectures ago. But it's so thin that everything basically comes down to a horizontal line, and we don't enter horizontal lines in our fill table. So you can go through computing your fill table and end up with an empty fill table. And you have to account for that in your code, or crashes occur. It's generally best, in my opinion, this last one is kind of an opinion case here. At some point, you do have to round everything down to essentially an integer x and y so you can plot it. But it's best to round your x and y coordinates that you store in the fill table, but do not round the dx, of course, because it's fractional. So while you're going to round your endpoints, store your rounded endpoints in your table, keep everything as real numbers. I know in Python, I think it automatically keeps everything as real nice floats. But in some languages, you can choose to have integers. Don't make them integers, or that's going to screw up all your math, because even though you've got to treat it as an integer when you're going to plot it, right? If you're calculating the slope of a line, you want to know what the x really is, including fractions there as you move from line to line. When you go to plot it, you have to round because it's got to go to a pixel. But if you round it to a pixel and use that value each time, it would screw up your edges. They would look bad. Questions. In terms of a polygon, what should we use for the edge column? Andrew, can you verbally explain that? Because I don't know what you're asking me there. Oh, I think I see what you're saying now. Nothing. That's not really stored in the table.
Okay.
Yeah, I mean, it's in the table, so I can talk about what edge there is. But this is 0, this is 1, this is 2, and you don't need a name for it.
Yeah, I'm just trying to think about how to iterate through this. And I'm imagining we can use just a array for the x start, y start, end, and slope, and then have an array of arrays for the table.
It's an array of arrays. Remember, this is Python, so it's a list of lists.
List of lists.
It's a two-dimensional array is what it is.
Okay.
Or again, it's a list. In Python, it would be a list of lists. Okay, let's look at the code, because Mike is a nice guy. Well, actually, let's look at the pretty little picture here. This is actually generated by my code. Okay. The algorithm's not hard, but it's delicate. It's delicate. You're going on a first date with this algorithm. You want to treat the algorithm with extra care. okay? Because first dates can go horribly wrong, or they can set you up for a lifetime of pleasure, okay? So we want this to be a good experience. So you have to be careful. Here is the polygon fill algorithm in extremely detailed pseudocode. It takes in a polygon and some color that you want to paint the polygon. First thing you have to do is do our backface test that we wrote. Backfacing polygons are not drawn, so if the polygon's not visible, then you just return. That was easy. If you're going to paint a polygon that's a backfacing polygon, you don't do any work because you don't draw it, so you don't paint it. Next, convert the polygon vertices to projected display coordinates, round them, but do not convert them to integers. So I'm going to call it display poly is project and convert to display, which is going to be a method that's going to call project, and it's going to call convert to display. Of taking in a poly and returning all of the points of the polys that have been converted to projected display coordinates. I'm not going to respond verbally, Andrew, to your last comment. I will just chuckle. Next, we pre-compute. So, throw away backfaces. Well, when you find a backface, just exit. There's nothing to do in painting that poly. Convert everything to display. Again, I'm rounding everything, but I'm keeping it as real numbers. So round, but do not convert to integers. Extremely important. Pre-compute the edge table constants that we just talked about. X start, Y start, X end, and DX. Compute that for each of the edges and store them in a table. I broke that out into compute edge table where we're passing in, of course, the polygon in display coordinates. This is how you prevent some crashes from occurring. If the edge table is empty, then return. And that can happen with, like I said, very short or very thin poly. Basically, if everything just gets down to horizontal lines. And again, if you're viewing a polygon that's almost edge on, then because we are rounding our X and our Y's, you could end up with a polygon. You can have a polygon that's less than 1 pixel thick, right? And if that happens, it'll generate a blank edge table because everything will show up as a horizontal line, and so the edge table will be empty. And if the edge table comes out empty, if you start indexing things in it, you're going to get an index out of bounds. So this is basically, yeah, the polygon visibility test didn't catch it as not really facing me, but dude, it's edge on, so you're not going to see it anyway. All right. Painting proceeds line by line from the first line, from the first to the last fill line. Okay. So where do we start and where do we end? Well, the first fill line is the Y start value of the first edge. It's probably not going to look like this in code because your edge table, you're going to be indexing it with 0, and then there'll be the Y is what column? Y is the second column, so it would really be something like edge table 0, 1 here. But I'm writing this in a way that it's easier to read. This is pseudocode. I'm not giving you the actual solution in Python. So that's the smallest Y start in the edge table. The last fill line will be the largest Y start in the table. Again, this is not in any recognizable language. This is Mike O'Neill trying to tell you you have to find the maximum Y end in all the table. And that's the last fill line. You then need a couple of indices. You need to know I, that's the index into the table of one of the active edges, J, that's the index into the table of the other active edge. And then next is simply the next edge in the table, which we'll set to 2. So I starts out at 0, J starts out at 1, next starts out at 2. So we're going to go between edges I and edge J. We don't know which of them is left and which of them is right, but since we've sorted the table by increasing Y start values, we know the first 2 edges, edge 0 and edge 1, are going to be the active edges that we're going to draw between. Okay? All right. So now we know the indices of the active edges. I'm going to call them edge I and edge J. So edge I, the X component of it, edge J, the X component of it. Edge I, the X component, is the X start value of edge I, and edge JX is the X start value of edge J. Okay, so now I've got names for my active edges, edge I and edge J. Here is where we begin the actual paint routine, and I've been saying all along that you've got an outer loop and an inner loop. And so here's the outer loop that goes from edge to edge, from fill line to fill line. From fill line to fill line, we're painting one fill line at a time, from first fill line to last fill line. So this is how we move down, one line at a time. Okay, now let's look at what are you going to do when you're trying to paint a line. Well, first we have to determine which edge is left and which edge is right. So if edge IX is smaller than edge J sub X, then the left X is edge IX and the right X is edge JX. Otherwise, they are the opposite. Left X is edge J and X right is edge I. We just flip them one way or the other depending on which is smaller. So now we know at this point our left edge, the X value of our left edge, and the X value of our right edge. So we want to paint across the fill line. So as X goes from the left X to the right X, here's where the magic happens. Create line from XY to X1Y with fill color, whatever color you passed me. That sets a pixel. You set all the pixels across the fill line here. X1, X2, X3, X4. So our X is moving up each time by 1, right? And that's how we move across the fill line. Okay, so we filled the line. Now we got to get ready for the next line. So update your X values for your 2 edges. How do you do that? Well, you just take the current edge IX and add in the DX for that edge. That gives you the updated edge X value for I. Do the same thing for J. Multiply that edge JX. Add to it the DX for edge J, and that'll give you edge JX. So we updated our left edge X value. We updated our right edge X value. Oh, I'm not referring to them as left and right. Well, because at this level we only really know that they're edges, and we have a DX that's associated with edges. We need to talk about this, but when we get back up at the top of the list, remember the first thing we do in every pass is we figure out which is left and which is right. So we're updating our edges here. In fact, this code is general enough. I said that we weren't going to do complex polygons with the edges that cross. I think I've built this robust enough that even if the edges did cross, the algorithm would still work, which is nice. Makes it a little more flexible. I didn't test that. There might be some little bugs here, but in general, since we're testing the left edge and the right edge every time at the top of right before we do a paint, it should work even if the edges cross. Okay. So what's left? Well, what's left is when you reach the bottom of an edge, you have to switch that out with the next edge. You can reach the bottom of an edge, right? And have to bring in another edge. So if Y, remember Y is our line from first fill line to last fill line. So if Y, the current fill line, if that's greater than or equal to the end of edge I, and if you haven't reached the end of the polygon itself, yeah, I discovered this as I was writing my code because I was getting an index out of bounds. When you reach the bottom of your polygon, you're going to reach the end of both edges at the same time. There are no new edges to add because you're at the bottom of the polygon. So if I'm not at the bottom of my polygon, right, and I've reached the end of an edge, then you have to switch out that edge. So I is assigned the value of next. Edge IX is get the X start value of this new edge, and then don't forget to increment your X, your next, to point to the next edge in the table. That's if Y was greater than or equal to edge I. Maybe edge I drops out, maybe edge J drops out. You have to do the same test here. It's possible if you've got a polygon with more than 4 edges in it, that both of your active edges could drop out at the same time, and you could go to 2 additional active edges. What do you mean here, Mike? Well, remember those polygons that we drew a few pages up, if I can go to them. This guy. These 2 edges drop out at the same time and are replaced by these 2 edges. And these 2 edges drop out at the same time and are replaced by these 2 edges. So if you've got a polygon that's got more than 4 edges in it, you can be executing this code that it can't. You have to independently test both of the edges here to see if either or both fell out. Okay? All right. Notes. Remember, this algorithm operates in projected display coordinates. You'll want to round your coordinates, but not your dx, please, to the nearest pixel. But you don't want to use integer math, because that'll throw everything off. This algorithm tends to run very, 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 very slowly. On my old laptop, it takes about a second per screen refresh, given a scene with 2 cubes and a pyramid. I promised you I would run it for you. Here is code written by an old man who never programs, okay? If I can do this, you can do this. If we go and we look, we see that, hold on, this is what things look like in wireframe. The cube is behind the pyramid, so you can't see it. But if the cube is the active thing, and it is, if I start bringing the cube backwards, where are you, Mr. Cube? Oh, am I moving the pyramid? Oh, yeah. Don't move the pyramid that way, Michael. Okay, let's, oh, I've got that. Let's move the pyramid forward a little bit. And let me now switch over to the rectangle, and let me go back to mode 3. So now I should be on the cube. Hopefully, yeah, you're beginning to see the cube. You can see, barely starting to see the corners of the cube start to poke through the pyramid here. And it goes slowly. It takes, oh look, the front of the cube is just coming through the front of the pyramid now. And this geometry is correct, okay? We are passing the cube through the pyramid. This is the way it is supposed to look as the cube moves through the pyramid. And eventually, most of it, the top of the pyramid is still sticking out here. If I were to move the cube, say, down, I could do that. Okay. Andrew's asking, why are the vertical edges so heavily artifacted? Because they're not exactly vertical. And if you might go, oh, this looks crappy. Remember, this is 400 by 400 pixels. There's not a whole lot of pixel resolution here. We're keeping the object small, so you're going to see artifacts. Also, if I go back to mode 1, you will notice that this is the built-in edge draw. It is just as rough, pixelated as the edges that I draw. So again, I'm not drawing edges, but the edges that you see based on my fill. My fill is no worse than what's built in. Okay. Let's see. So I'm reading Eric's comment. He's asking about why is it so slow. The reason why it's so slow, the main reason why it's so slow, Eric, is that line right there. Because we don't have access to the canvas, we cannot draw a pixel directly on the drawing canvas in tkinter. Okay, that's blocked off to us. We're having to go through a back door to set a pixel, and we are using a high-level line draw command that we are reducing to a pixel set. Okay, and so by doing that, we are drawing. Think about it. We're drawing thousands of very, very, very tiny lines. That's why it's slow. If we had the ability to directly set a pixel, this thing would run much, 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 much faster. Even though, we're manually at the Python, and Python's an interpreted language, so it wasn't built for speed. But we're at a high level language. The polygon fill, the algorithm that we're covering, is generally implemented right at the hardware level, right? So the algorithms that we're learning these algorithms for a reason, and the reason is you need to know how polygon fill works, okay? So we're implementing the algorithm. But in reality, that algorithm would be pushed down to the hardware level. The other reason why we're going through this is ZBuffer, which I see that's going to slop over into Monday. ZBuffer depends on exactly this fill algorithm. So like I said, we're pretty much out of time today, so ZBuffer's got to wait. We finished fill. This is all I have on fill. The next part is ZBuffer. But here I want to sneak ahead and show you. Well, let's just glance at things. We got a polygon fill table again. We got equations that look almost identical to the equations that we talked about. It's in polygon fill. Oh, but look, instead of just dx, we now have a dz. Oh, so we're adding a dz. Oh, and we still have the d. Oh, and look, we got the dz is just z start minus zn minus z start over n minus y. It's the same thing. You just swapped out z for x. And if we get down to the actual implementation of the algorithm, this is the polygon fill that I just went through, and what I highlight in green, these are the only changes you have to do to the algorithm to add z-buffer. So z-buffer becomes a part of polygon fill, and it works just like the other parts of polygon fill. So if we hadn't gone through polygon fill, you wouldn't be able to do z-buffer. That's why we're doing this. And here's another thing that is true. When we finish this, we're going to go, as I alluded to at the beginning of the lecture, we're going to start talking about painting polygons to make them look smooth, where we are painting the color of each polygon, of each pixel, a pixel at a time. That's how we're going to do that. It's going to go in the fill algorithm, and it's going to use equations almost identical to what we've been doing here. You're going to look at them and you're going to say those look extremely similar, and they'll be implemented in a very similar way. And that's why it's one of the reasons why, look, I've never given a class. You guys are an experiment, okay? I have never given the class the level of detail that I am giving you guys, right? I wrote the program myself last weekend, and after writing the program, I went back and said, okay, from this program, let me go and write pseudocode for, if I can ever get there, let me write pseudocode for polygon fill, right? I know this code is solid, because there'll be a typo in it, there can be a typo in it. This pseudocode is very solid because I wrote the friggin' program, and then I went back and wrote the pseudocode from the program. I catch all the problems for you, like empty polygon fill tables and problems that people have, like where to know the difference, how to know which edge is left and which edge is right. How do you swap out an edge? I've solved all the problems for you, okay? So your job will be to take this and translate it into Python. Having written the program, though, it took me hours to debug it, because a little thing, like if you go through and, right, you round in the wrong spot, or you swap an I for a J, you're only going to be able to find that if you really understand the algorithm and trace through it. So my expectation is that you'll take this, you'll code it up, and then when you try to run it, it won't run. And then you'll have to try to figure out, okay, where did I go wrong? And that's going to cause you to go through a debugging process in which you'll learn how the algorithm works. That's what I'm hoping. I'm also hoping that pretty much everybody gets the code working properly, because the problem I've had in previous instances of this class is half the class doesn't get this working perfectly. They get it working halfway, and then they can't do the next assignment because it depends on this working perfectly. So I'm trying an experiment with you guys. Am I giving you too much and making it too easy? Or is this the right level of complexity that'll get most of you through? We're going to find out. Okay. We are out of time, so I'm going to let you guys go. Any of you have, and you see why I'm so worried about the fact that, a third of you didn't attend this lecture? I don't know what they're going to do. Anyway, I'm going to let you guys go. If you have any questions, I will stick around after I stop the recording. But other than that, have an excellent weekend.